So today we're going to do a little bit of factoring, and this is specifically called out in the SOLs that we're supposed to be able to factor sum and difference of cubes. It's a new formulas that we haven't seen yet. They're like the last ones that we really get in terms of factoring. And then we have to learn about this thing, which has the fantastic title of the fundamental theorem of algebra, right? So it must be important if it's got a title like that. Now, before we do that, let's refresh ourselves on this stuff. Right? Let's do another. Use the calculator to enter data, look at the data, and then decide what kind of function it is, right? And then once we know, we're going to make an equation. So remember, you want to go stat, edit. Let me see. Maybe we need new batteries. Okay. Remember, we're going to go stat is this button right here, right? And then you hit edit, and then put your data. L1 is for the X values, L2 is for the Y values. Right, while you're doing that, I'll do it too. You see how I do that? Yeah, just put in the values. So all the X's go there. So 15, 17, right from that. Okay, once you do that, you got to look at it, right? Okay, grab that. What's going on with these calculators? Right? Once you've got the data in there, you got to look at it so you could determine what's the shape of the graph. You know, which function should I use? Remember, first you got to turn on the plotting of points if it's not already turned on, right? Where do you look to turn on the plotting of points? Yeah, the second y equals, and that very first one, if it doesn't say on already, then hit 1 and hit enter to turn it on. Okay, how do you make the calculator show the points you just entered? Zoom 9, which is zoom stat. Okay. Run stat, edit, and you're not in L1 and L2. You need to go stat, setup editor, enter, try it again. Okay, so once you turned on, then you go zoom 9 to look at the points, right? If you just went to the middle of the graph, you would not have seen these points because I made them all the way to the right. They're not in the middle, right? If I did, let me take this off first, clear. If I went to the zoom 6, just the middle of the graph, you'd say, well, where's my points? That's why you do zoom 9, and it goes right to the points that you just entered in the calculator. Okay, now, what kind of function does that look like? That's linear, right? So after you've made that decision, then how do you make the model? How do you make the equation which will model that data? Stat, and then you arrow over to calc, and which option you're going to pick? 4 for linear, right? Because we think it's linear, we're going to go 4. Now yours has a slightly different screen there, which is fine. But you're going to end up getting linear reg, ax plus b. And when you hit enter, you should see that. Did everybody get that? If you didn't, say something. If you're not trying, then nothing I can do for you. How could I put that equation without having to hand enter it? How could I enter that equation onto the y equals? Do you remember what I showed you on that? Go to the y equals. Make sure it's clear. I can only take you so far with this because this one doesn't do the same thing as yours does. But if you go to the y equals and you hit the vars key right there, V-A-R-S, and then remember which option you pick under vars? Statistics, right? Because that's where you put the data, stats, right? 5. And then what do you do on that screen? Arrow over to the EQ. And that REG, that is the equation you just made. That's the regression. Remember, it's called lin-reg. Okay, there's the equation. When you hit enter, it puts your equation on that line. It may not look like it, but it is. Hit graph now. See, if I do mine, it probably doesn't. No, that actually worked for the linear. You should see the line going pretty close to through the points. If you do it, then I'll go here. Y equals vars 5 for stats, arrow over to the EQ, enter, and it could go there again. Vars. Did you make your, I don't think you did this. Go stat, calc, 4 for linear, enter, till you go all the way to the bottom, go. Okay, there's your regression equation. Now, y equals. Then you go vars 5, EQ, enter. And now hit graph. Is everybody getting a line? Looks pretty close to that? Okay. So there was the equation. Like, you could have written it down like that, just substitute for the A and the B. If you have to use this equation to make an estimate, how would I make an estimate of the value when x equals 18? What are they asking you to do? What does y equal and x equals 18? How are you going to do that? Well, in general terms, when it says find the value of y when x equals 18, it means plug in 18, right? It means take that and put it in there and calculate the y. But again, if you've already put the equation in your calculator, you don't really have to do that. You can go to the calculator and just go to the table, which is above graph, second, and then scroll down to, what did we say, 18? And you got your y value. There we go. 3.6257. About y equals 3.63. Okay, how about if I wanted to know the value of y when x equals 40? I mean, again, you either plug it in there and calculate, or go to your table of values, and you're going to have to go down to 40. I might have a problem with that, but that's all right. There we go. Negative 6.28. Right. That's the last step in the SOL is, you can model data, you can pick an appropriate model, you can model the data, and then you can make a prediction using your model. That's what that's about. Okay, there was another thing we did last time, which was this stuff. And these are the exact problems that we looked at. We're supposed to understand what it is for a graph to increase or decrease. Increasing means that it's going up from left to right. So this would be an increase, this would be a decrease, this would be another increase. Right? When you name where it's increasing or decreasing, you're always naming the intervals of x, meaning don't use y values, use x values. Right? So this thing is increasing from the left side of the graph all the way until it gets to this point right here. And what is the value of x there? -1. So it's increasing for x is less than -1. Right? It's increasing for x is greater than 1. And then in between -1 and 1, It's decreasing. So I wrote it like decrease, -1 is less than x is less than 1. Okay, that was one thing we did. And I did the same thing for these three. We did it in class last time. What I'm going to give you this time, I'm going to give you a handout, part of the homework, which is going to have this on one side. And then on the other side will be 4 that are blank. You know, it's just got the graph, but it hasn't marked the intervals. I want you to do that part of it. Right, so here's the increasing and decreasing. That's this part. Right. The second part is identify the zeros. Where do you look for the zeros on a graph? We already talked about this. The x-intercepts, right? So all you have to do for that part of it is circle the x-intercepts. These are the zeros. 1, 2, 3. 1, 2, 3. For linear, just 1. And quadratic, 1 and 2. Right. And then the last thing, indicate the end behavior. And for end behavior, we're just going to do like the book says, because the book, that's the way this book is doing it. It's not necessarily wrong. The end behavior is to describe what's the graph doing on the right side of the graph over here and over here. Right? So on this side, it's going up. Just say up. The end behavior is up on the right, down on the left. Right? What is the end behavior here and here? It's 2 ups. Up, up, and up. What's the end behavior here? Down and up. What's the end behavior here? Down and down. So that'll be one side of the piece of paper. The other side, this is already on one side, and the other is like 4 for you to mark up in the same way and hand in at the end. Let's go back on blue. Okay, the new stuff for today starts right now. Jose, you paying attention? Okay. So we haven't finished with factoring yet, right? Factoring, remember, we factor expressions so that we can solve equations. Yeah, we do some factoring for the sake of factoring, but it's in the end just so that we can solve some equations. Right? In the last chapter, chapter 4, we factored quadratics primarily. Right? And quadratics mean the degree is 2, right? The highest power of x is 2. So this would have been a standard form of a quadratic, right? The highest power term on the left, decreasing order of powers, no parentheses, right? This is the factored form, right? And we factor it so we can use, remember what the property is? The property says that when you multiply things and you get a 0, that means one of the factors is 0. It's called zero product property, right? Zero product property. So since x minus 3 times x minus 2 is 0, then either x minus 3 is 0 or x minus 2 is 0. So x equals 3, x equals 2. 2 answers because it's quadratic. I mean, that's an example. That's why we learn to factor, so we can solve equations with this method. Right? And these were all the different methods that we used in Chapter 4. Most of them are specific to quadratic functions. Right? GCF, what did GCF stand for? Greatest common factor, right? So GCF, greatest common factor, difference of squares, meant something like x squared minus 4. How did that factor? X plus 2 times x minus 2. Okay, what did I mean by a simple quadratic trinomial? Okay, well, the number is 1, so you don't see it, right? If in a standard form of a quadratic, you have ax squared plus bx plus c. If it's simple, that means a equals 1. So that was just like this one here, right? A was 1, so we just had to have a one-step factoring process. What are the factors of 6 that add up to -5? And I picked -2, -3. Okay. And the not simple then was when A does not equal 1. And we had to go through that 5-step process for that. So these were all the things that we did in chapter 4. We don't add much new in terms of factoring in this chapter. I'm sure everybody's done. Yeah. Eleven. Okay, we done with that? Tanisha, you done? Okay. So here's the new kinds of factoring that we do in this chapter, right? We do GCF. GCF can work for any polynomial, any degree. So there's a little bit of GCF. The way I write it there, it's GCF plus, because usually it's a GCF, and then there's a little bit more to do. And then the two new ones for sure are called sum and differences of cubes. Sums of cubes, differences of cubes. We're ready? Okay. Let me know if it's too fast. So for example, if I had to solve this cubic equation by factoring, then I would first look for a common factor. Do you see any common factors in all three of those terms? There's an x, right? And that's usually the case, right? There's got to be a power of x that if you take it out, you end up with a quadratic inside, so you can use one of your other methods. So first step, I would have taken an x out, and then inside I would still have x squared minus 3x minus 54. And then what kind of factoring could you do inside the parentheses? Come on. Shouldn't be so hard. What kind of factoring are we going to do inside the parentheses? What is the value of A? Inside the parentheses. Come on. Simple quadratic. Simple quadratic. So you can think, if you can think of factors of negative 54 that add up to negative 3, then you can factor this. And they are x minus 9 times x plus 6. Okay, now we can solve this like we did in the homework last night, right? What are the values of x? What are the zeros? X equals 0, 9, and negative 6, right? You got an x here. So you got, remember, you got one of the zeros is 0, and then you got 9, and you got negative 6. Right? If you looked at that in the graph, and you should be really, always looking on the graph, it would have looked like this, right? You can see there's clearly a 0 there at negative 6. There's clearly a 0 there at 9. You might not quite see what's going on right there, right? But it is there. It is going through the graph right there, and you can verify that in the table of values, right? Second graph, and just scroll to find where is y equals 0, and y equals 0 at negative 6, at 0, and at 9. Okay. Okay, let's try to do the same thing on this one. What is the greatest common factor on the left? Say again. Close. 3x squared, right? Because the lowest power of x there is x squared. Everything has an x squared. And everything is divisible by 3. So factor out a 3x squared. And what's left inside is x squared minus 2x plus 4. Okay, is what's inside factorable? It's another simple quadratic, so you have to say to yourself, are there factors of 4 that add up to -2? What are they? I mean, the factors of 4 are 1 times 4 and 2 times 2, or -1 times -4, or -2 times -2. Do any of those add up to -2? No. So it's not factorable. So what other method can you use if it's not factorable? Quadratic formula, right? You got to remember, quadratic formula is the only one that always works, and it's given to you. So definitely you go there. So this is what this will look like if I do quadratic formula. It'll be x equals -2 plus or minus the square root of -2 squared minus 4 times 1 times 4 divided by 2 times 1. Right? That's substituting a equals 1, b equals -2, c equals 4. Okay, simplify. X equals -2 plus or minus the square root of 4 minus 16 over 2. Right, which is x equals, I made a mistake there, didn't I? Sam, you were supposed to catch that. -2 should have been a +2. You just going to let me keep going like that? Okay. Okay, so now this is 2 plus or minus the square root of -12 over 2. Okay, so what kind of solutions are we going to get here since we're taking the square root of a negative number? You're going to get imaginary solutions here, right? Remember that the square root of 12 is the square root of 4 times the square root of 3, right? 12 is not a perfect square, but if you factor it, 4 times 3, at least you could simplify the square root of 4 part, right? That's 2 times the square root of 3. So this thing, x equals 2 plus or minus 2i times the square root of 3 over 2. And then you could divide the 2 into both terms. So this is x equals 1 plus or minus I root 3. Okay, now compare this to the graph, right? There's our 4 answers that we just got. We got x squared means the 0 is 0. What's the multiplicity? 2. And what do we expect that to look like on the graph? It looks like it comes down and it hits the x-axis at 0, but it stays on the same side. Exactly what we expect because of the multiplicity, even power, right? But it never crosses the graph again, right? Because those last 2 zeros are imaginary. And you wouldn't expect to see them as x-intercepts on a number line, which is all real numbers. Right? You only see the real solutions here. So the imaginary solutions are not going to show up on the graph. So that points out the 2 things, the multiplicity and the shape on the graph. When you see that, that means your 0 came from a factor which was to an even power. And then the fact that you're not seeing all 4 of the zeros on the graph, that just means they're not real numbers. Okay, I think we have to come back to that in a minute. Okay, then that gets us to the other kinds of factoring that we learn in this chapter called sum and difference of cubes. And by sum of cubes, we mean when you add things that are cubes, right? A to the third plus B to the third. A is being cubed, B is being cubed, right? And you're adding them. That's why it's the sum of cubes. Right? The difference of cubes just means you're subtracting them. Now they have very similar formulas. Right? They are, for the sum of cubes, it's a plus b is the first factor. And then it's a squared minus ab plus b squared for the second factor. And notice for the difference of cubes, it's almost identical. What's the only thing that's changing in between these two formulas? This plus becomes a minus. This minus becomes a plus. Everything else is the same. Remember that the last term, always positive. Always positive. You shouldn't have a negative ever is the last term. The way I always remember it is like this. If it's the sum of cubes, then you expect that first factor, which is a binomial, to be a sum. If it's the difference of cubes, then you expect that first factor, the binomial, to be a difference. And then the sign that follows is opposite. So that plus becomes a minus, that minus becomes a plus. Everything else is the same. I would say on the SOLs, there's probably like 3 questions about this stuff, whether it's a factor for the sake of factoring or a solve an equation with this. So let's look at some examples. X to the third plus 1. Before I factor it, let's write it as the sum of cubes, because right now it doesn't look like a to the third plus b to the third. How could I write 1 as a cube? See, this one could be a tricky one. That's a to the third plus 1 to the third. Sorry, that's x. Right, that's x to the third plus 1 to the third. Because 1 to any power is still the same thing. So now I've written it as a sum of cubes, use the formula, right? So we're going to use this formula on top. Okay, what is it in our problem that takes the place of a? X, right? And what is it that takes the place of b? 1. So everywhere here where you see an a, put an x. Everywhere you see a b, put a 1. So that'll be x plus 1 times x squared minus 1x plus 1 squared. Right, notice the pattern, right? It's the plus matches with the plus, and then that sign is the opposite of it. Right, and this first term is x squared. The next term is 1x, so I just write x. The next term is 1 squared, which is just 1. Right, how could I write x to the third minus 8 as the difference of cubes? What number cubed equals 8? X to the third minus 2 to the third. Right, 2 times 2 is 4, times 2 is 8. 2 to the third equals 8. Jose, right, you're snoring. Okay, so now in our formula, what is it that takes the place of a? X, and what is it that takes the place of b? 2, not negative 2, right? You're not substituting ever with the negative. The negative is part of the formula, so just substitute. X minus 2 times x squared plus 2x plus 4. Good. Jaden? Tanisha? Good. Okay. How could I write 8x to the third plus 27 as the sum of cubes? Again, we just saw what number cubed equals 8? 2. So I can write the first term like this. 2x in parentheses cubed, right? That'll cube the 2 and cube the x, right? And then 27 is what number cubed? 3. 3 times 3 times 3 is 27. Okay, so what is it that takes the place of the a in our problem? 2x. And what is it that takes the place of b? 3. So just substitute for a and b. Right? It'll be 2x plus 3 and 2x squared in parentheses minus 2x times 3 plus 3 squared. And you can simplify that. That would be 2x plus 3 times 4x squared minus 6x plus 9. How about the bottom one? I'm stressing your capability to know your cubes. What number cubed equals 64? 4 times 4 times 4. So that's 4x cubed. And how about 125? What number cubed equals 125? 5. 5y cubed. So, and this time our a is 4x, our b is 5y. So substitute in the formula. This is the difference formula. That would be 4x minus 5y times 4x in parentheses squared plus 4x times 5y plus 5y squared. Right, and then I can simplify that. 4x minus 5y times 16x squared plus 20xy plus 25y squared. Well, you guys finish writing that. I'm going to hand out these again. If you notice, these, which have the multiplication tables, also have the perfect cubes at the bottom. Understand? Okay. Yes. What's that? Okay. We're ready? Janine, you ready? So you got to know your perfect cubes, right? If you don't know your perfect cubes, it's hard to recognize one of these problems for what it is, right? If you recognize these numbers, then when you see them in the problem, you know, right away you think, okay, they're using a cube, it's probably one of those formulas, right? But if you don't recognize it as that, you're probably looking at it going, you know, this doesn't look like it's not a GCF, it's not a difference of squares, it's nothing, you know, that I can think to factor. But if you know these numbers and look for them, then you'll realize what it is you're being asked to do. Now, I give you this sheet in our class. On the SOLs, you won't necessarily have that. However, Remember, you can always make your own table of squares and cubes. Just go to your calculator, right? Go to the y equals, and let's just say we want the cubes. Then put x to the third, and go to the table of values. Second, well, let me set my window to 1. Second table, right? So there's 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, right? So you can make these. If they weren't given to you, you can still like just make some of them and write them down so that you can look at them when you're looking at these problems. I'm good with all the ones through 6. I always remember. These I don't always remember. 1,000, 10 times 10 times 10. I think I can remember that one. Okay. So most of the time, if you get a factoring problem that's like this, and it's in a multiple choice format, what you usually see is that there's some kind of dead giveaways. It's not like you have to remember the exact formula. For example, this one here, this is a difference of cubes. And if you recognize 216 as 6 to the third, then you might think, okay, I should be looking for the first factor as x minus 6, since it's a difference of cubes. All right, the first one is not right because it starts with x plus 6. So you throw that one out. Right? The next one has the x minus 6, but it's got the wrong sign there. That's supposed to be a plus. So you throw that one out. Right? The next one, we know this is supposed to be a binomial times a trinomial. It's not going to be 2 binomials. It can't be right. Throw it out. Right? So the only one that's left is the right one. That's D. I find that most of their problems, you can eliminate 3 out of the 4 just by, it's not in the right form. And just take the one that's left. Did I write that down? No. We're good. Okay, so we're going to get these kind of problem, right? Solved by factoring. And you should look at it and say, well, this is going to be that kind of factoring, which is a difference of cubes, right? Because I recognize 8 is a cube, 2 to the third. So I factor this. That is x minus 2 times x squared plus 2x plus 4 equals 0. Okay, and then I look at this x minus 2. You say, well, what are the solutions? What is the solution that comes from the factor of x minus 2? What is the 0? There's 2, right? So x equals 2 is going to come from that. And if you look at the graph, you can see it, right? It goes right through x equals 2. If you need it, you can confirm in the table of values. But remember what the shape of a cubic is, and that was a cubic. It has 2 turns. And you can see on this graph, it's got the 2 turns down here. And it's got the 1, 0 there. So it's not going to have any more x-intercepts on here. Cannot happen. So what kind of solutions are we going to get from this other factor? Imaginary, right? And that's always the case. When you do the sum and difference of cubes, the trinomial there is never factorable. It's always going to involve I, right? So I have to, this one I have to do quadratic formula. Right, x equals negative 2 plus or minus square root of 2 squared minus 4 times 1 times 4 divided by 2 times 1. And that equals 2 plus or minus 4 minus 16. This is the same one we looked at before. So we know that this ends up being 1 plus or minus 2i times the square root of, oh, sorry, that's wrong. right? We've solved that one already. And that's always the case, right? The trinomial there is always going to have imaginary solutions. You're just going to get one, and it comes from that first factor. So that leads us to the second part of what we're doing today. And before we get to that slide, exactly, there is a theorem called imaginary root theorem. It has different titles, but the imaginary root theorem says that the imaginary roots, also known as zeros, occur in pairs. For example, on the last slide, because of the plus or minus in front of the square root, right? We had two solutions that come from that. -1 plus I root 3, -1 minus I root 3, right? When complex numbers, imaginary numbers differ just by the sign in between, those are called conjugates. Okay. And we know there's no way we could get one of these as an answer without the other, because we know where it comes from. It comes from the quadratic formula. So when we're looking for how many imaginary zeros we should get, we know it's always an even number, right? Imaginary zeros always occur in pairs. So the number of imaginary zeros are always even. You need that before you go. Okay, this is the side I've already done. Then you try to do the same thing on that side. Okay. We're good. All right, now the fundamental theorem of algebra, again, big name for a theorem, says that we expect exactly as many, I got to amend this, complex zeros as the degree. Again, now the distinction, these two words, roots, zeros. Zeros are for functions, right? Zeros are the values of x that make the graph hit the x-axis, make the y equal 0. Right? When you don't have a y in an equation, right, then it's called a root. Roots and zeros. They're used interchangeably, and I would guess that about half the people don't even know why they use two different words for it, but that's where it comes from. So for example, if we have a linear, because it's x to the first, we would expect 1 complex zero. For a quadratic, because it's x squared, we expect 2. For a cubic, because it's x to the third, we expect 3. Whatever's the highest power, that's the degree. That's how many complex zeros that you've got. Right? That's not to say that's how many x-intercepts you've got. I mean, we've already seen in the last chapter, every parabola doesn't cross the x-axis. Right? So now we're going to try to make the distinction between, okay, well then, how many real zeros could there be and how many imaginary could there be? We know they add up to the degree, but how many of each could there be? We done? Okay. Okay. So the number of complex zeros means the real and the imaginary. All added up together, how many zeros you get, that'll be the degree. The real zeros are the x-intercepts on the graph. Right? That's what you look for. You look for the x-intercepts on the graph. Why did I have that there? Right. Taking into account multiplicity. Right. It could be, if you see that it hits the axis and goes back on the same side, you know it's actually there twice. Then the imaginary zeros, we know, are always going to be an even number. And then it'll be whatever the complex zeros are minus the number of complex minus the number of real has got to be the imaginary zeros that are left. Okay. So for these 4 problems, and your homework has these same directions right here, so you're going to do them exactly the same way. Looking at number 34, what is the degree? 3. So how many complex zeros are you going to have? Absolutely, you have 3. Whatever is the degree, that's how many complex zeros you have. Now, remember, imaginary zeros have to occur in even numbers. So how many possible imaginary zeros could you have? Could you have 1? You can't have 1, right? You can't have 3, but you could have 2. If you had 2 imaginary zeros, how many real zeros would you have? 1, because they got to add up to 3, right? Okay, well, what else? What if you had 0? 0 is an even number. If you had 0 imaginary, then how many real would you have? 3. That's what these are looking for. They want you to list the possible number of real and imaginary solutions, given that they have to add up to the degree, which is the number of complex. Try the next one, 35. It's another cubic. I mean, these things are only going to change, right, by the degree. Everything else is going to stay the same. So we can say that since this is a cubic also, there's 3, and you could have 2 or 0, 1 or 3. Right, but okay, here's a quartic. How many complex zeros do we have for a quartic? 4. Fundamental theorem of algebra says exactly 4. Okay, well, how many different even numbers could we find in between 0 and 4? 0, 2, and 4. Okay, well, if you had 0, imaginary, how many reals would you have? You'd have to have 4, right? And if you had 2 imaginary, how many reals would you have? 2. And if you had 4 imaginary, then you would have 0 reals. And of course, because this one is the same degree, those numbers repeat themselves for that problem. Now, when it comes to finding the actual zeros, not just the possible number of zeros, but actually finding the actual number of zeros, that's a little bit of detective work, and it's not so clear all the time as you're doing it. Okay. I mean, your homework when it comes to is just going to be just like that. I think you got 4 problems like that, and it should go really quickly. Good, Taylor? Oops. Okay, so let's do the same drill first for this one. It's x to the 5th, right? So how many complex zeros does it have? 5. Right? How many possible even imaginaries could you get? How many even numbers are there between 0 and 5? It's 0, 2, and 4, right? It could be one of those. If there were 0, then how many real numbers would there be? There would be 5, right? If there was 2 imaginary, then there would be 3. If there was 4 imaginary, then there would be 1. Okay. In fact, this is the graph of this one. So let's see. You know, usually you look at the graph to say, okay, well, the number of real looks like it's just 1, right? But that's not actually what that means, right? Remember, you see the graph go right to the x-axis. It doesn't mean it's raised to the first power. It means it's raised to an odd power. So you might look at a graph like that and say, oh, I think I've got 1 and 4. That's the combination. That is actually not on this problem. This problem is f of x equals x plus 1 to the 3rd times x squared plus 25. So the 0 here is -1, and it has a multiplicity of 3, right? Which means on the graph, it'll go through -1, it keeps going, because raised to an odd power, it will change sign when it gets to that 0. And the other zeros would come from this. But generally, you know, the way you find actual zeros is you look at the graph and find those real zeros, and then you do something which we didn't do in this chapter because you don't have to, so we didn't, which is we learn how to divide polynomials. So you divide out all the real zeros so that you just left with something with imaginary solutions. But we're just going to worry about the numbers of zeros that we would expect, because that's the SOL. So let's see. Factor polynomials by applying general patterns, including differences of squares, sum and difference of cubes, perfect square trinomials. So the thing that we added that we didn't do yet, because we've had this objective before, is the sum and difference of cubes. And the next one is sum and difference of cubes. And then given a polynomial equation, determine the number of real solutions, the number of non-real or imaginary solutions. Okay. Right. So I'm going to give you a worksheet. It will be part of the homework, right? And on one side, it's got all the increasing and decreasing, circle the zeros, end behavior. You try to repeat on the other side and turn it in next class, right? This homework here, page 301, that's 2 solve equations that are sum or difference of cubes. And this one is a It's those like the last four. How many possible real? How many possible imaginary? And we have a quiz next class over the first couple days of stuff.